Imagine standing beneath a clear night sky, feeling the cool air against your face. The stars stretch in every direction, shimmering points of light scattered across a vast darkness. You might find yourself wondering if beyond that darkness, other minds are asking the same questions you are. Not grand pronouncements, just a quiet, steady curiosity. In 1961, an astrophysicist named Frank Drake formulated a way to estimate the number of detectable extraterrestrial civilizations in our galaxy. He wrote down a simple equation that breaks the problem into smaller pieces. Each piece represents a factor involved in the emergence and detectability of intelligent life. It's called the Drake equation, and it's often written as n equals r x x n x f l phi x c x l, or represents the average rate of star formation in our galaxy. Astronomers have measured star birth happening throughout the Milky Way, and while the exact number varies, they generally agree on a few stars per year. Standing in your backyard, you don't see new stars being born, but you know they're out there forming in massive clouds of dust and gas. FP stands for the fraction of stars that have planetary systems. With the development of advanced telescopes, such as those monitoring subtle dips in starlight, thousands of exoplanets have been discovered. These findings suggest that planets are common, not rare. People once imagined planets as special treasures. Now it seems that almost every star is orbited by at least one planet, many of which might be small and rocky. Ne represents the number of planets per star that could potentially support life. A planet's location matters. If it's too close to its star, surface water evaporates. Too far away, and oceans freeze into ice. There's a comfortable middle ground called the habitable zone, where conditions could favor liquid water, our key ingredient for life as we know it. Observations show that many stars host planets within these zones. Fel is the fraction of those habitable planets on which life actually appears. Life requires complex chemistry, stable conditions, and enough time to get started. On Earth, life emerged relatively early, given the planet's age. Microbes took hold in ancient oceans and never surrendered. Yet no one knows if life sparks easily, or if Earth's success was a fluke. It could be that life emerges whenever conditions allow, or it could be vanishingly rare. Phi is the fraction of life-bearing planets where intelligent life evolves. For billions of years, Earth's creatures were simple. Complex animals appeared late, and thinking beings even later. Intelligence might be a difficult step, requiring just the right evolutionary pressures, or maybe it's a common outcome, a natural progression once life gets going. We don't know. FC is the fraction of intelligent civilizations that develop detectable communications. After all, a civilization can be intelligent without building radios, telescopes, or spacecraft. Earth's radio broadcasts began a mere century ago, a blink in cosmic time. If alien civilizations are out there, but don't construct technologies to announce themselves, we have nothing to detect. Finally, L is the length of time such civilizations remain detectable. A civilization might discover radio waves, broadcast signals for a few centuries, and then fall silent. The universe is ancient, and timing matters. Two civilizations could exist in the same galaxy and never overlap in time with active communication. The Drake equation doesn't give a single definitive number. Instead, it's a framework. Researchers plug in values based on observations and research, then see what comes out. As our understanding of stars and planets improves, we refine FP and N. Discovering microbes in extraterrestrial oceans or signs of life in exoplanet atmospheres would help refine FL. Understanding intelligence on other worlds or the longevity of technological species remains guesswork. There was a time I visited an observatory late at night. Just me, a dim red light, and the quiet hum of a tracking mount pointing a small telescope at a star. I reminded myself that almost certainly was orbited by planets. Some of those might have oceans. It's a calm feeling, knowing we've left behind the idea that we're unique. Yet the telescope offered no clues beyond faint light. If life were there, I couldn't see it, couldn't confirm it. That's the direct consequence of the Drake equation's uncertainty. It focuses attention on what we need to learn: the nature of planets, the frequency of biology, the likelihood of intelligence, and the persistence of technology. Each discovery in astronomy, biology, and geology reshapes the numbers we put into it. Data from telescopes and space probes steadily chip away at the unknowns as we map more exoplanets, measure their atmospheres, and seek biosignatures. We place tighter constraints on landfall, signals of artificial chemicals, or light patterns on distant worlds would provide data for FEA and FC. I recall reading about astronomers who point radio telescopes at promising star systems. They scan a huge range of frequencies for anything structured. So far, they've found only cosmic hiss, pulsar beeps, natural phenomena. This continuous silence makes you think about the lifetime of civilizations. It's a reminder that even if signals are out there, they might have ceased centuries before we had ears to listen. The Drake equation's structure lays out the path. It's all there. How fast stars form, how many have planets, how many of those can host life, how often that life becomes intelligent, how often it communicates, and for how long. Each factor's value changes as we learn more. Each new measurement of exoplanet abundance, each discovery of extremophile life in Earth's harsh environments, each insight into the chemical complexity of organic molecules in space, all contribute. Watching researchers work is like watching puzzle pieces come together one by one. Though the final picture remains incomplete, we know the Milky Way contains hundreds of billions of stars. With modern telescopes, we have found planets everywhere we look, suggesting that the fraction of stars with planets is high. We've identified potentially habitable zones around many stars, fueling the idea that habitable planets aren't unique to our solar system. Our own planet's ancient rocks hold fossils of microbes that thrived billions of years ago, hinting that life might begin whenever conditions allow. Still, from that first cell to beings who think, speak, and build radios, that's the hardest part to pin down. The silence we currently experience could mean that detectable civilizations are rare. Or maybe we haven't looked long enough, or in the right way. The Drake equation never promised answers, only a structure to guide questions. It highlights data we're missing and pushes research forward. The ongoing discoveries of exoplanets, molecules in their atmospheres, and the study of early Earth conditions all help refine these factors. Picture yourself now, holding that knowledge under a star-filled sky. The Drake equation sits quietly in the back of your mind, a reminder that each pinpoint of light could host worlds full of life or stand empty and quiet. The equation never claims certainty. It simply catalogs what we must consider: star formation rates, planetary abundance, habitable worlds, life's emergence, intelligence, communication, and lifetimes. Its presence encourages you to gaze upward, to listen intently, to be patient, and to keep refining the numbers. It all unfolds beneath that silent, twinkling canopy overhead.